Earlier in the module, we introduced the concept of an amphiprotic substance. And an amphiprotic substance, we said, is one that can act either as an acid or a base. And the question is, how do we know which one it's going to act as? And basically, you have to look at what it's reacting with. If it's reacting with something that is a stronger acid than itself, then it's going to act as a base. If it's reacting with something that's a stronger base than itself, then it's going to react as an acid. I mean, that seems like it should be relatively clear, but how do I actually tell if I'm looking at Kas or, if I'm just looking at the two formula, how am I going to be able to tell which one it's acting like? Well, there is a relationship that can help us out. For a conjugate acid-base pair, and remember, the conjugate acid-base pair is one where you have two formula that are related by a hydrogen ion. So NO3 minus and HNO3, which is that's a strong conjugate acid-base pair. So we would be looking more at the weak ones. CH3COOH, which is acetic acid, related to CH3COO minus. Okay, so that's a conjugate acid-base pair that would play into this. Whenever I take the Ka and the Kb for a conjugate acid-base pair and I multiply them together, it's going to give me Kw, which is the water ionization constant, which is 1 times 10 to the minus 14th that you learned when we talked about pH before. Okay, so this is the relationship between the two. Strictly from a mathematical perspective, if this number, if Kw is always 1 times 10 to the minus 14th, so you know that that's always what that's going to make, always. If Ka gets bigger, what has to happen to Kb? It has to get smaller because I'm going to multiply the two of them together to get this. If Kb gets bigger, Ka has to get smaller, okay? So we can use that mathematical relationship between the two of these to compare weak acids and weak bases and figure out how things are going to react. So let's look at example 7.7. And I don't know how far you've read. If you've read the section after the on your own box, the trick that I'm going to show you is one that he has already mentioned there. I don't know how clear it is in the way he words it, but he goes to a lot of work in solving this problem that you do not have to go to. So I want to make sure that you understand how to compare these Kas and Kbs so that you don't have to do all this calculation. All right. So first of all, the first part of the question says, write an equation for the reaction between HSO4 minus and KOH. Well, if you look at this, this is certainly not anything. I mean, it looks like an acid because it's got an H on the front of it, but this is not on our list of strong acids. In fact, H2SO4 is a strong acid, but this is not. Just because this is the conjugate base of a strong acid does not mean that this also is strong. In fact, it is certainly not strong. It is very much a weak acid. This, however, is a strong base. Potassium is in the first column on the periodic table. So anytime you have either a strong acid or a strong base reacting with something else, it is going to go to completion. So that is what's going to happen in this particular instance. So I'm going to have HSO4 minus plus KOH yields single arrow because I have a strong base. If this is a strong base, then this is going to act like a base. This one's going to act like an acid. So what that is going to give me here is I'm going to have a sulfate ion, SO4 2 minus, and this is going to split up. And so this is going to give me K plus, and the OH minus is going to combine with this hydrogen over here, and that's going to give me a water. Okay, so that is the equation for the first one. Okay, if that was a little fuzzy as to where this came from, I want you to think about it this way. The KOH splits up into K plus and OH minus when you put it into water. Okay, so once that splits up, there's the K plus. The hydrogen ion from here comes over and joins this OH minus, and then that's where the water came from. All right, so complete reaction because I had a strong base in this one. But now let's look at the second part of the problem where they're asking you to write an equation for the reaction between HPO3 2 minus and HCO3 minus. Neither one of these is strong. They're both weak. And so how am I going to determine whether this guy donates the hydrogen this direction or whether this one donates a hydrogen ion and it goes this direction? How am I going to know which one is which? Well, they gave me the Kas, but they didn't give me the Kas of what they wanted reacted together. What they gave me is the Ka of the conjugate acid of these. So here's HPO3 2 minus. This is H2PO3 minus. So this is the conjugate base of this acid. Similarly, HCO3 minus, and this is H2CO3. So if this is the acid, this is the conjugate base of this acid. All right, so that's the comparison that I have to look at. Of these two, which one is the stronger acid? Well, the stronger acid is the one that has the larger Ka. Which one of these has the larger Ka? Well, the larger Ka is this one because 7 is bigger than 4.3. They both have the same exponent over here. So therefore, the Ka of this tells me that this one is the stronger acid. This is going to be the weaker acid, okay? From what we know over here, we know that the stronger the acid, the bigger the Ka, the smaller the Kb. So the stronger the acid, the weaker the conjugate base. Now this is only for conjugate acid-base pairs, but that's what we're dealing with over here. So that means this is the stronger acid. So if this is the stronger acid, that means that this one is the weaker conjugate base. If this is the weaker acid, this one is the stronger conjugate base. Okay, you see where I got that? If this one's strong, this one's going to be weak. If this one's weaker, this is going to be stronger. So now, when I react these two guys together, I have HPO3 2 minus plus HCO3 minus. And because they're weak, it's going to be an equilibrium reaction. So I've already determined that this one is the weaker conjugate base, and this is the stronger conjugate base. So which one acts as the base? Yeah, this one does because this is stronger. So this is going to donate its hydrogen ion here. This is going to act as the acid. This is going to act as the base. So this donates its hydrogen ion, and I will end up with PO3 3 minus plus H2CO3. Okay? Does that make sense how I got that? Hopefully it does. You look at your Kas, determine which one is stronger. Notice that the stronger acid goes with the weaker conjugate base, and then the weaker conjugate base is the one that is going to act as the acid down here. Or another way to think of it, the stronger conjugate base is the one that acts as the base. So that is how I am able to tell what the final reaction is there. So as you're working through these problems and writing formula, make sure that you recognize two things. First of all, the Kas that they give you are going to not be the same as what they give you up here. So don't look at it too quickly and confuse that. And then secondly, a stronger acid means a weaker conjugate base. And so that's how you're going to be able to reason through that and determine it. There's no need to go through all the calculations. All right, so I'll let you practice that.